So a lot of what you read had a lot of jargon and terminology. And I thought it would be fun to start by getting on the same page in terms of that terminology. So when we talk about the quantum realm, let me use Lisa's term, quantization is a really big concept. So can someone tell me what they think of when they think of quantization and why it might be important for us? In the quantum universe, you can only access discrete energy states. So in our everyday world, I'm standing here, and I walk over here, and that is a continuous process. I don't just suddenly appear here. But in the quantum universe, electrons can't do that. They can't continuously move from one energy state to the next. They appear at each of them. What's fun about this for us is that this quantization of energies of electrons and other particles, it's really useful for encoding information in a binary digit system. So, right, the ground state of my atom or whatever particle can be the 0, and the excited state can be the 1. And what you're going to see is a lot of the qubit systems that we're going to look at work exactly like that. You're using the ground state as 0, and you're using some excited state as 1, and you're doing something to push between them. The handy thing is that the ground and excited states can be our binary digits. All right, so where things get weird is when we think about this aspect of quantization and the idea of superposition. So what is superposition? That's something we talked about last time, and it's critical to understand for this class. So this fun little animation is from NIST, and it was in the Soto article, and it's showing skateboarder and saying, okay, skateboarder's here, but in a quantum universe, it can be in both places until I look at it, and then it collapses to one of them. And it's not really exactly being in two states at the same time. It's being in a linear combination of states at the same time, where the coefficients of that linear combination dictates the probabilities of being in one state or the other, right? So that was our A and B coefficients in our wave function last time. David Wineland, who received the Nobel Prize in 2012 for his experimental work in this field, he gave the analogy of superposition as, so he deals with trapped ions, which we'll hear about from Sarah later in the class. And he gave the analogy of his trapped ions being a marble in a bowl. So the marble can roll back and forth, and in normal times, it will be on one edge of the bowl, or I'll roll it over to the other edge, and it'll be there. But what's cool with these trapped ions and other qubit systems is that you can create a scenario where it is in a superposition of both states. That is what allows it to act as a 0 and a 1 at the same time, whereas ordinary bits of data can only be 0 or 1 at any given time. That's why qubits can hold more information, exponentially more information than a traditional bit. So the problem with superpositions is that they're very fragile. They don't hang around easily. Doing anything to them can potentially break them. Certainly measuring them breaks them, right? We know that. That's kind of by definition. But there's lots of other things that can, break my superposition. And those things are generally called decoherence. So anything that breaks my superposition. So it's something in the environment. It could be something even in the qubit itself, not to mention, temperature or something in the environment that causes a superposition to be destroyed. So you're saying, okay, I'm not measuring it directly, but I might be observing the system heat up, or I might be observing light move in a goofy way over here. So I'm kind of indirectly observing it. So that you are influencing, you're perturbing the system, and those are the things that can potentially break the superposition. They're also the things that are potentially interesting about the superposition. So it is, as we'll see more, it's quite delicate. And that's why nearly all of these systems operate at, the non-optical systems at least, operate at really low temperatures, like dilution refrigerator temperatures below helium. Yeah, it's interesting, this issue that you're bringing up in traditional computing. As the size of gates gets smaller and smaller and smaller, we get to nanometer separations between gates, and so then they kind of become quantum because tunneling becomes kind of operational at those length scales. The last, maybe most weird, big buzzword in all of this is entanglement, and so that's this sort of quantum marriage between qubits. Somebody want to explain how they think about entanglement? So two particles share some fundamental part of themselves so that no matter what distance they are from one another, particle 1 influences what particle 2 is doing. So imagine you have an ion, this like trapped ion acting as a qubit, and it's in a superposition of 0 and 1, and I entangle it with a second ion that's also in a superposition of 0 and 1. The two entangled ions are going to maintain this special relationship even if they're separated by a really large distance from one another. So as an example, if this kind of weird relationship can mean that the two particles will end up in the same value, either 0 or 1, when I measure one of them. So measuring one of them impacts the state that I'll measure for the other one. That's pretty weird. And I think some of you may have heard this term that Albert Einstein coined long ago called spooky action at a distance in quantum mechanics. And this is the kind of thing he was sort of describing. So if I measure the value of one qubit and it determines the value of my second qubit. And that's why in quantum information, having one qubit by itself isn't actually very useful because it is 0 or 1 when you measure it. But having two qubits, I can measure one of them and I haven't touched the other one, so it can still do useful things for me. It can still tell me about the first one, even though I've measured it. All the A, B, theta, phi, all those fun variables. Yes, okay, so quantization, superposition, decoherence, and entanglement. Those are kind of the big things that we're going to discuss in this course over the next several weeks, once we have our bearings about us. All right, so there are some other fun terms that were brought up in some of these readings. So one of them is quantum supremacy. The idea of quantum supremacy is it's basically a goal of demonstrating that a programmable quantum computer can solve a problem that no classical computer could solve in a feasible amount of time. All right, so what's interesting about this idea of quantum supremacy, so this concept was coined by John Preskill in 2012. And the annoying thing about it is that the problem that the quantum computer solves doesn't have to be useful. So it can be a toy problem, and you can still claim quantum supremacy. And so there's been this really fun to watch punching match against different quantum companies, mainly Google and IBM, being like, I showed quantum supremacy, and then IBM's like, no, you didn't. Yeah, so for example, in 2019, Google said, okay, we took our 54-qubit quantum computer, it looks like that, and we reached quantum supremacy. We had 54 qubits, 53 of them actually worked, and we did a series of operations in 200 seconds that would take a regular supercomputer 10,000 years to do. They validated and verified that, stood by it, and then IBM walked in and was like, that's an excessive claim, because if you use our supercomputer, they had the best one at the time in 2019, it's called Summit, that their supercomputer can do the calculation that the Google quantum computer did in 2.5 days. So not quantum supremacy. there's also been a claim in 2020 by a Chinese team out of the University of Science and Technology in China. They were using a photonic quantum computer, so very different looking than Google's quantum computer. And they were able to show that they could do Gaussian boson sampling with 76 photons. And they could generate the number of samples the quantum computer could generate in 200 seconds would take a classical computer 2.5 billion years. So that one still stands. And there's several other examples of these photonic quantum computers, so playing with entangled light to do boson sampling, that stand. So there's a couple examples from USTC, and then there's one from the company Xanadu, which I mentioned last class. So one thing that's interesting about all of these quantum computers is that none of them are useful. None of them can do useful problems yet. And it's because of this second part of the title of this slide. It's because we're in the, what is this called? Noisy intermediate scale quantum era. So we not yet at a number of qubits that's useful for doing anything, that's able to do anything useful, including be fault tolerant and error correcting. So generally, people kind of define the NISQ era as being up to about 1,000 qubits. People think that once we get to beyond 1,000 qubits that we'll be able to do something useful, but we're still pretty far from that. And that's one of the big reasons that all qubits are on the table, right? The problem is that when you keep adding qubits to the system, decoherence gets easier and easier and easier. Like you mess up one piece of the circuit, it's all done because it's all entangled. Yeah, so as you add more qubits, you need more qubits to do error correction, and more qubits, yeah, so it gets very complicated. Programming quantum computers is a whole field in itself, as the people that are more computer science-y in the room know. There's a whole department or division over there in computer science thinking about this. Not trivial. So we as, or me at least, as the material maker person, or material measurer person, is very much thinking about, okay, how do I prepare a pure two-state system that doesn't decohere fast? And then there's the people in the programming side of things thinking, when I have 1,000 of those, how do I tell them to interact? How do I get information out of them when they're interacting? So, two crazy, hard problems. Yeah. So it's because the 2 to the n, so 1,000 qubits can behave like 2 to the 1,000 bits, and that's big enough to do something useful. Okay, so here's another. Yes, we will. Okay, so there's this thing between the qubits we actually have, which are not logical qubits. Logical qubits are perfect. They work as they do on paper in theory. I'm not even sure we have one logical qubit. Yeah, okay, yeah, so that's right. Some of the ion trap stuff is, but only like 1 or 2. So this idea that the 53 working qubits in Google's system, yeah, they are pretty good, but they're not acting like, like you would write when we write sort of the interaction matrices and things for qubits. They don't behave perfectly. So when a qubit behaves perfectly, it's called a logical qubit. You would need 1,000 logical qubits to do something pretty useful. Again, that's why we're pretty far away from this goal at this point, yeah. So what's fun when you start thinking about this field is that there's a lot of really cool history that sort of led up to it. Quantum computing feels like this very new topic, but it's, kind of based in super old ideas in regular computing, right? So in 1936, this is when sort of Alan Turing, published his paper on computable numbers. And this was sort of in response to an earlier paper on the Hilbert problems. And in his paper, he described something called a universal computing machine. A lot of you, probably have seen movies about this. And that is the thing that became the Turing machine. And in 1980, so many years later, this is Paul Benioff. He kind of used Turing's paper to propose theoretical feasibility of quantum computing. The paper that he wrote to kind of show this, if you want to look it up, for example, is called The Computer as a Physical System, a microscopic quantum mechanical Hamiltonian model of computers as represented by Turing machines. And it was the first one to demonstrate that it's possible to show the reversible nature of quantum computing as long as the energy dissipated in the system is arbitrarily small. So that comes back to our decoherence issue. And then in 1981, this is when Feynman came around and was thinking about this stuff. And he showed that quantum mechanics could not efficiently be simulated on a classical device, which kind of set the stage for the goal of quantum supremacy. So when he was kind of going around talking about this stuff, he made the very famous quote that a lot of you probably have heard of, nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. It's not so easy. And so that's why when you hear a lot of, especially computer scientists, talk about quantum computing, they always go back to how nature works, like how nitrogenase converts nitrogen to ammonia, or how hydrogenase works, because those are such complex systems, and we couldn't hope to understand them without a quantum computing kind of platform. And then, let's see, last person to mention in this kind of short timeline is probably around the same year, 1981, 1982, David Deutsch produced a description for a quantum Turing machine, and he designed an algorithm created to run on a quantum computer. And from there, it was all kind of set off. So after that, then we get, Shor and Grover and David Wineland and all these people. We're going to learn about their algorithms later in the class that came up with clever strategies to demonstrate quantum supremacy and to come up with kind of simple problems that could be solved with simple quantum computers. So it's a pretty fun history, and there's a lot of big players in it, which is cool to see. A lot of these people are still alive, which is also interesting. All right, so one of the other things I had you all read was this National Strategic Overview for Quantum Information Science. And one of the big things that kind of grounds this report is the desire to create or to educate a quantum smart workforce. Yeah, so you need a workforce that's ready to take advantage of the power of quantum computing and quantum computers. And what does creating a quantum smart workforce require? So the report kind of has some ideas about this in it. All right, so yeah, two big prongs, K-12 education, university investment, plus industrial partnerships, industrial university partnerships. This one, I think, is pretty evident from all of us sitting here. I mean, you are part of the quantum smart workforce. But this partnership with industry is pretty important because they're on the ground and kind of know what exactly is needed. What do we need to know to do what they're doing? How do we need to be able to communicate to be effective, at Google in their quantum division. The one that I think is kind of interesting is the K-12 education piece. Do you think that elementary school kids could learn something useful about quantum mechanics? Everything we told you is wrong. In college, let's start all over when our brains are already cemented and we already thought we knew what was going on. 100%. I think this is a really important point. Kids are so smart. I have an 8-year-old, and I'm constantly flabbergasted at what she could do when she was 3. And she's learning algebra now because she goes to fancy math schools that do these things. And I'm like, man, I didn't learn that till high school. So yeah, kids are very capable of grasping things, especially because they don't have any preconceived notions about what's weird. Yeah, I think that this is such an interesting thing. I think that even when we go out on K-12 outreach, I think we underestimate the youths. I think that we still need to learn how to talk to them with words they'll understand. But I think they can understand some pretty sophisticated concepts. And if you started early enough, I think that we would get kids in college and coming into grad school that this was all not weird to them at all. So I do really like that point. And I think it wasn't necessarily developed as well as it could have been in the report, but I do think it's pretty important. So a few other things in the report that I think are worth mentioning are the fact that to really capitalize on the quantum, on what's coming along in quantum computing, we have to support these other technologies that are going to be absolutely essential for them working. So things like cryogens. How many people have heard that getting liquid helium is hard? Everybody, right? Yeah. There's, especially if you go the photonic quantum computing direction, really sophisticated, photonic, super fancy lithography kinds of things are needed. Microwave amplifiers, other types of nanofabrication. Yeah. Any other quantum supporting technologies that you think weren't necessarily listed in the report? The other thing that I thought was interesting about the report is, it takes a very nationalistic viewpoint on why we should be doing this. And the things they list are first, military capability, second, economic productivity, and third, international competitiveness. And maybe international competitiveness is up there higher. How do you guys feel about that? It is interesting to see what academics, put in the intros of their talks versus what is kind of in the intro or in the, priority list of this report. Yeah. There are very many positive applications, for sure, even in defense and military. But, I don't disagree. I don't disagree that that's why they put it here. It is terrible. And, as a scientist, I think about things like this a lot. I think about, so I've talked about nitrogenase a few times, and the classic example of Fritz Haber's discovery of the Haber-Bosch process, and that enables 50% of the population on the planet to exist, and 50% of the nitrogen in our body comes from that industrial process. But all of the research that went into that, enabled chemical warfare, and he was not a good person. So there's a lot of interesting ethics to think about in this field as well. And maybe the last thing I'll leave you all with is, because we're kind of on that topic, and we just have a minute left, is this last one. So Soto brought up this interesting idea about accessibility and economic inequality as this technology really comes online. What did you guys think about that? Yeah, it's going to be interesting, and this stuff's going to happen in your lifetime, right? So I'll be very curious. There's other perspectives on this, right? There's perspectives that this is all hullabaloo, and there's going to be no quantum revolution. So, I'm not going to take sides, but we're in a class on quantum information, so let's talk about it. But I think there is, this is all the world in which this does happen. And there is a world in which it doesn't happen because of the things we talked about at the very beginning. So